Bismillahirrahmanirrahim. Okay, so I shall review first a little bit, okay? So, this chapter we're talking about rational functions. So, first we actually learned several different things. We learned indeed how to simplify rational expressions, right? And we also learned this trick to make sure we don't fall for excluded values and stuff. And this means basically don't fall for it. Certain numbers you have to exclude because the denominator cannot be 0. And then we learned about rational functions, and the parent equation was this. And the general equation was this. Right? Easy enough. The last part of this was solving rational equations. Okay. And the basic principle there was getting rid of the denominators. Right? And that was that. So I want to just do one example as a review. One example as a review. It's always good to review. So the parent function is this, right? Y equals 1 divided by x. Correct? And y equals negative 1 over x. It's going to be a what? A mirror image. Another way of saying that, more proper way of saying that, it's a reflection about what? About the x-axis, right? So if this is the parent equation like this, that's y equals 1 over x, then this one is going to be a mirror image. Another way of saying that is this is a reflection about x-axis, right? Grab the hole? Okay. Right? Now when you move a function this way or this way, okay, that's called a shift. If this way is called a horizontal shift. Right? So you have horizontal shifts. Another term for shift is, what's another term for shift? Translation. Correct? So you can take a function and move it this way, and that's called a horizontal shift. And if you move it this way or this way, this is called a vertical shift. Right? Or vertical translation. Does that make sense? Now, if you make the graph chubby, like this, right? You follow? And you can make the graph chubby by increasing the numerator, right? Right? That's the stretch. Right? So that's called a stretch. And if you make the graph skinnier, that's called a shrinking. And that's made by making this smaller. Does that make sense? So when you compare graphs to the parent graph, let's do this, okay? Now, how would you compare this graph to the y equals x, right? How'd you compare that? Okay, you look at one at a time. Okay, first, what does this do to the graph? The negative sign. It's a reflection. So this graph is a reflection of the original parent function, right? Okay, so what does the 5 do to this? We'll go this way. What does the 5 do to this? Yes, it's a stretch, right? Compared to the parent function. What does the 3 do to this? Omar. You again. Which way? Horizontal shift, right? Goes this way. This is Vx moves it horizontally. Vy moves it. So what is? So it's a horizontal shift 3 units to the right, right? And so what? Vertical shift or vertical translation by how much? Vertical shift by how much?
4.
By 4 units, right? So it's a reflection about the x-axis. It's a stretch, right? It's a vertical stretch like this. You can say vertical stretch, all right? Compared to the original graph, it's a horizontal shift of, or horizontal translation of 3 units, and it's a vertical translation or vertical shift of 4 units. Does that make sense? Easy enough, right? Okay. So that's that. Okay. All right, let's, Abdul, it's your turn. Let's solve this equation. Okay. Abdul, what are we going to do? We're going to solve this. So when we have these rational functions like this, our goal is what? Yes. How do we do that though? Yeah, you want to get rid of the denominator. You're fine, Michelle. So the objective here is to get rid of the denominator. They make your life harder, right? Okay. But so we have to do that. So how are we going to do it? So multiply the whole equation by, right? Right? By what? Which is what? So you want to do multiply both sides like this by 2a plus 8 like this?
I just want to top.
Good try though. Your intentions were good. But before you multiply, you try to do what? What if the denominator was like this? You multiply the whole thing by that? No, right? You try to factor it out, right? Right, you try to factor out denominators, right? Is there anything you can factor out here? Yes, you can factor out a 2, right, from here. What? 4, right? Yes, yes, yes. Okay, so now you factored out, see? Now what do we do? Now you can multiply the whole equation, see? By what? A plus 4 and 2, because that's also a plus 4. You're done, right? Right? Okay, so now what? And then this, and you have to multiply to every single term, right? Make sure you do it. Now what? What do I get? So just do progressive logical reasoning, right? So I have a plus 7 times a plus 4 times 2 like this over a plus 4, right? Then I have minus 1 times the whole thing, right? So 1 minus 1 times, I'm going to put 2 times a plus 4. Is that cool? And I have a plus 10 times a plus 4 times 2 over 2 times a plus 4, right? And then what do? Chap. I get rid of these, right? This? You can't. So negative 1 times 2 is just negative 2, right? So now what do we have left here? We have 2 times a plus 7, right? Minus, there's a 2 over here, times a plus 4, right? And then over here we have just a plus 10. Now we have to solve this, right? Well, how do I do it? I'll give you a hint. What is this? This is called distribute. You distribute, right? Yes? Okay. What do you get when you distribute? What about here? Minus 2a. Minus 8. Right? And then, whoa, this is nice. Simplify, right? What happens then? Okay, so what do you get? Yeah, these two cancel each other out, right? Okay, then, and then 14 minus 8? That's good, that's all it's does. 6 equals a plus 10. And then?
Subtract 10.
And then you get a equals? Negative 4. Ta-da, you're done, right? No. What do? You have to make sure that it's not a what? Excluded value. Very good. Is it an excluded value? Yes, it is. So you look for excluded value before you start chopping, right? If you put it over here, you get a 0, right? So this is an excluded value. Then what? We're stuck. We don't have any solution. What do you say? No solution. Very good. All that work for? Nothing. No. It didn't lead us to the wrong path. Does that make sense? You always have to look to make sure the solutions are not extraneous solutions or excluded values. Does that make sense? Okay. That's how you solve rational equations. And I'm sticking by it. So, let's let those